freely. He further found that when the whole of the free oxygen had been used up, fermentation proceeded vigorously, but was accompanied by comparatively little yeast reproduction. From experiments of this kind, made with several organized ferments and under various conditions, he was led to the discovery that whilst certain organisms were only capable of living when supplied with plenty of free oxygen, others could survive the total deprivation of that element, and when so deprived appeared to function most actively as ferments. From this he was led to conclude that there was a very intimate connection between the phenomenon of fermentation and life in the absence of air. Organisms which required free oxygen he called aerobic, and those which could live without it anaerobic. Yeast was an organism capable of living under both sets of conditions, but it was only as an anaerobic that it functioned at all actively as an alcoholic ferment. It may be of interest to quote Pasteur's own words. Fermentation by yeast, that is to say, by the type of ferments properly so called, is presented to us, in a word, as the direct consequences of the processes of nutrition, assimilation and life, when these are carried on without the agency of free oxygen. The heat required in the accomplishment of that work must have necessarily been borrowed from the decomposition of the fermentable matter, that is, from the saccharine substance, which like other unstable substances liberates heat in undergoing decomposition. Fermentation by means of yeast appears, therefore, to be easily connected with the property possessed by this minute cellular plant of performing its respiratory functions, somehow or other, with oxygen existing combined with sugar. Its fermentive power varies considerably between two limits fixed by the greatest and least possible access of free oxygen which the plant has in the process of nutrition. If we supply it with sufficient quantity of free oxygen for the necessities of its life, nutrition and respiratory combustions, in other words, if we cause it to live after the manner of a mold, properly so called, it ceases to be a ferment. On the other hand, if we deprive the yeast of air entirely, or cause it to develop in a saccharine medium deprived of free oxygen, it will multiply just as if air were present, although with less activity, and under these circumstances its fermentative character will be most marked. In a word, the yeast cell required oxygen for its vital activities, and if deprived of free oxygen would obtain that which it needed by breaking up the fermentable sugars and utilizing the oxygen which was supposed to be liberated in the process. This theory of life without free oxygen was almost universally accepted as an explanation of the process of fermentation for a period of nearly 30 years, although it obviously did not supply a very clear insight into the mechanism of the change. It purported to tell us why the yeast cell decomposed the sugar, but not how it did it, and had any chemist been challenged during that period to state more precisely what occurred when the sugar molecule was broken up into alcohol, carbon dioxide and other substances, he would probably have referred it to some special vital force resident in and indissolubly connected with the living protoplasm. In 1892 Adrian J. Brown, in the course of an investigation on certain phenomena connected with the reproduction of yeast, obtained some results which rendered the life without free oxygen theory quite untenable. By applying for the first time the hematometer to the counting of the cells, he found that when yeast was introduced into a fermentable liquid such as wort, the cells increased to a definite number for a given volume, and then ceased to multiply. The limit of increase was within certain limits independent of the food supply in the liquid, and also of the number of cells originally added, provided that the number did not exceed the maximum number to which the cells would increase under normal conditions in the liquid in question. If, on the other hand, a number of cells exceeding the maximum were added, little or no multiplication occurred. Hence, by working with the number of cells in excess of the maximum, multiplication could be avoided, and fermentation phenomena could be studied under conditions which practically eliminated that disturbing factor. Working this way, Brown found that aerobic conditions did not inhibit fermentation, but that on the contrary a plentiful supply of free oxygen actually stimulated it, and so was forced to the conclusion that Pasteur's view could no longer be upheld. There can be no doubt that the yeast cell does require free oxygen for its development and for the purpose of carrying out its life activities, and although its fermentative vigor may appear for a time to be independent of that element, a fresh supply must be forthcoming or the yeast will languish and die. In 1897 a further and very great advance was made in our knowledge of the nature of the fermentation process, for in that year E. Buchner showed that the liquid contents of the yeast cell, when added to a fermentable liquid, are able to excite fermentation without the presence of any cells at all. He ground up pressed yeast with quartz sand or kieselguhr so as to rupture as many of the cells as possible, and after adding a little water and wrapping in a cloth, subjected the mixture to a pressure of about 500 atmospheres (3 or 4 tons per square inch). In this way he obtained a clear, slightly opalescent liquid, which when added to a solution of sugar very soon brought about its fermentation, precisely as if yeast itself had been used. At first it was objected that small particles of living protoplasm had passed through, and that it was in these that the fermentation activity resided. This, however, was shown not to be the case, for not only could the expressed yeast juice be evaporated to dryness at a low temperature without losing its activity, but it was capable of bringing about fermentation in the presence of certain substances such as chloroform and arsenites, which are protoplasm poisons and are known to exert a powerfully inhibitory effect on the life of the cell. As further proof that living protoplasm was not in question, it was found possible to filter the juice through a Chamberland filter without destroying its activity. From these and many other experiments, Buchner concluded that fermentation was the result of the activity of an enzyme secreted by the yeast cell, to which he gave the name zymase. As in the case of other enzymes, the activity of zymase is very dependent on external conditions. Thus when the yeast juice is heated to a temperature of about 50 degrees Celsius, coagulation occurs and the filtered liquid has no longer any appreciable action on sugar solutions. In the same way its activity is very greatly reduced or altogether destroyed by certain substances such as prussic acid. The next advance in our knowledge of the mechanism of fermentation is due to Harden and his colleagues. Harden found that when he submitted yeast juice to filtration through a Chamberland filter impregnated with gelatin, he obtained a filtrate and also a residue on the filter. On experimenting with these two portions into which the yeast juice had been resolved, he found that neither was possessed of any power of bringing about fermentation. When, however, the two portions were mixed, their activity was restored. In this way Harden was led to recognize that the enzyme, the portion which remained on the filter, is powerless to produce fermentation unless in contact with the portion which had passed through, the active constituent of which he designated the coenzyme. The solution of the coenzyme, the true chemical nature of which is still undetermined, retains its activity even after boiling. A further flood of light has been thrown on the nature of the fermentation process as the result of Harden's investigations on the effect of adding alkaline phosphates to sugar solutions in course of fermentation. Such addition was always followed by a rapid increase in the evolution of carbon dioxide, and it was found that a definite relationship existed between the amount of phosphate added and the volume of carbon dioxide liberated, a molecular proportion of the phosphate always resulting in the disengagement of a molecular proportion of carbon dioxide. An attempt to ascertain precisely what happened to the added phosphate in these experiments resulted in the discovery of a new compound consisting of hexose sugar residue and phosphoric acid, apparently having the composition C6H10O4 H2PO4 and designated hexone phosphate. When the phosphate is added to a fermentable solution in the presence of zymase and the coenzyme, it is supposed that one molecule of sugar, dextrose, breaks down into alcohol and carbon dioxide, whilst a second molecule reacts with the phosphate to form the hexose phosphate, the two reactions proceeding in accordance with the following combined equation: 2C6H12O6 plus 2Na2HPO4 equals 2CO2 plus 2C2H6O plus 2H2O plus C6H10O4 Na2PO4 . In practice it is well known that worts containing only a limited amount of phosphate, but relatively very large proportions of fermentable sugar, are capable of undergoing complete fermentation, and it is clear that according to the above view this could not happen unless the phosphate were in some way or other regenerated. Harding considers that the yeast cells contain an enzyme to which he has given the name hexosaphosphatase, the function of which is to effect the hydrolysis of the hexosaphosphate in the following manner: C6H10O4 Na2PO4 2 plus 2H2O equals C6H12O6 plus 2 Na2HPO4. Summarizing the above statements, the following may be regarded as the most recent view of the fermentation change. The enzyme zymase and its coenzyme together act on the sugar, hexose, in the presence of the phosphate, in such a way that one half of the sugar is decomposed into alcohol and carbon dioxide, whilst the other half unites with the phosphate to form the hexosaphosphate above referred to. The phosphate is thus rendered temporarily inoperative, but is liberated by the action of the enzyme hexosaphosphatase, which reproduces the sugar and phosphate, and so the cycle of change is ready to be repeated. This theory at least explains all the facts at present ascertained, but there can be little doubt that very much work remains to be done before we can feel satisfied that we know exactly what happens when a molecule of sugar is decomposed at the instance of a yeast cell. As in all cases where living organisms are concerned, the process is one of very considerable complexity, and compared with the apparent ease and rapidity with which the wonderful changes summed up in the term fermentation are accomplished by the yeast organisms, the triumphs of the modern organic chemist pale into insignificance. In the words of Professor Meldola, "When we can transform sugar into alcohol in the laboratory at ordinary temperatures by the action of a synthesized nitrogenous organic compound, when we can convert glucose into citric acid in the same way that citromyces can effect this transformation, then may the chemist proclaim with confidence that there is no longer any mystery in vital chemistry." Attention has already been called to the fact that the alcohol and carbon dioxide, although by far the most important, are not the only products of alcoholic fermentation, and it has been stated that glycerin, succinic acid, and various higher alcohols are formed at the same time. Recent investigations have thrown a great deal of light on the formation of these byproducts, and it has been found that some of them at least are not formed from the sugar at all. Thus, Ehrlich has shown that the higher alcohols, so-called fusel oil, result from the action of yeast on the amino acids, some of which are always present in maltwort. Leucine, alpha amino isocaproic acid, for example, yielding amylic alcohol. In this reaction ammonia, which is assimilated by the yeast, and carbon dioxide are liberated, and an alcohol is formed containing one atom of carbon less than the original amino acid. This reaction is probably of considerable importance from the point of view of the nutrition of the yeast, as it appears to indicate the means by which the yeast supplies itself with nitrogen in a readily assimilable form. The succinic acid, which is a constant product of fermentation to the extent of about 0.5%, appears to be derived from the dicarboxylic amino acid, glutamic acid. It has already been stated that some of the wild yeasts produce bitter products, and certain species, e.g. Saccharomyces anomalus, give rise to the production of pleasant-smelling ethereal substances such as are present in some fruit juices. It will, therefore, be understood that these byproducts are of more than scientific interest, since the flavor of a fermented beverage is not unfrequently dominated by them, and its commercial value either greatly increased or greatly reduced according to their nature. In addition to zymase and the hexosaphosphatase, the yeast cell contains a number of other enzymes, each of which has its specific function and all of which are of considerable importance in connection with the nutrition and life activities of the organism. Incidentally, some of these are, as will be seen, of considerable technical importance. So far as is known, the hexoses alone, and of these only four, viz. D-glucose, D-mannose, D-galactose, and D-fructose, are directly fermentable by yeast, and before fermentation of other sugars can take place, it is therefore necessary that they should be converted into one or other of these hexoses. This is in all cases effected by enzymes. Thus cane sugar is not directly fermentable, but has in the first instance to be converted by the enzyme invertase into a mixture of D-glucose, dextrose, and D-fructose, levulose, in accordance with the following equation: C12H22O11, cane sugar, plus H2O equals C6H12O6, dextrose, plus C6H12O6, levulose. Maltose has the same empirical formula as cane sugar and is, prior to fermentation, converted by the enzyme maltase into two molecules of dextrose. C12H22O11, maltose, plus H2O equals 2 C6H12O6, dextrose. Milk sugar, lactose, again, is not directly fermentable, but has first to be resolved by the enzyme lactase into two other hexose sugars, dextrose and galactose. C12H22O11, lactose, plus H2O equals C6H12O6, dextrose, plus C6H12O6, galactose. In this connection a point of considerable interest may just be mentioned in passing, namely that the enzymes exhibit a remarkable discrimination between certain carbohydrates which otherwise resemble one another very closely indeed. Whilst D-glucose, D-mannose, D-fructose, and D-galactose are fermentable, the optical isomerides of these carbohydrates, that is to say, forms which differ only in respect of their action on polarized light, are unfermentable. In order that a given sugar, other than the four above mentioned, may be fermented by yeast, it is essential that the yeast in question should contain the enzyme necessary for its conversion into one or other of the above hexoses. Now yeasts of different species do not all contain the same enzymes, and it therefore happens that a certain yeast may be capable of fermenting one carbohydrate and incapable of fermenting another. Of the enzymes, invertase appears to be the most widely distributed among the Saccharomycetes, and consequently the great majority of yeasts are capable of bringing about the fermentation of cane sugar. On the other hand, lactase occurs in only a comparatively small number of species, and consequently a great many yeasts, including the ordinary culture yeasts, Saccharomyces cerevisiae, are incapable of fermenting milk sugar. The following table may be of interest as showing at a glance the behavior of certain of the yeast species towards several of the more commonly occurring sugars. The sign plus indicates that the yeast in question is capable, and the sign 0 that it is incapable of bringing about fermentation. Yeast. Saccharomyces cerevisiae, dextrose plus, levulose plus, mannose plus, galactose plus, maltose plus, cane sugar plus, milk sugar 0. Saccharomyces cerevisiae Carlsberg, dextrose plus, levulose plus, mannose plus, galactose plus, maltose plus, cane sugar plus, milk sugar 0. Saccharomyces pastorianus, dextrose plus, levulose plus, mannose plus, galactose plus, maltose plus, cane sugar plus, milk sugar 0. Saccharomyces ellipsoideus, dextrose plus, levulose plus, mannose plus, galactose plus, maltose plus, cane sugar plus, milk sugar 0. Saccharomyces marxaranus, dextrose plus, levulose plus, mannose plus, galactose plus, maltose 0, cane sugar plus, milk sugar 0. Saccharomyces exogeus, dextrose plus, levulose plus, mannose 0, galactose plus, maltose 0, cane sugar plus, milk sugar 0. Saccharomyces ludwigii, dextrose plus, levulose plus, mannose plus, galactose 0, maltose 0, cane sugar plus, milk sugar 0. Saccharomyces anomalus, dextrose plus, levulose plus, mannose plus, galactose 0, maltose 0, cane sugar plus, milk sugar 0. Saccharomyces fragilis, dextrose plus, levulose plus, mannose plus, galactose plus, maltose 0, cane sugar plus, milk sugar plus. Kefir. dextrose plus, labulose plus, mannose plus, galactose 0, maltose 0, cane sugar plus, milk sugar plus. It may be that the secretion of any particular enzyme is, so far as is known, a very constant attribute of a given species, and that it has not been found possible by varying the nature of the food supply or the general environment of a given species of yeast to cause it to secrete other enzymes than those normally present. This selective behavior of the various species of yeast toward the different carbohydrates constitutes, in fact, a very valuable method of differentiation and identification. In addition to these sucroclastic, i.e. sugar-splitting enzymes, the yeast cell contains one or more proteolytic enzymes, that is, enzymes capable of acting upon protein matters and of converting them by hydrolytic changes into similar substances. Since the enzymes themselves are, chemically speaking, closely allied to the proteins, it might be thought that a proteolytic enzyme would attack the other enzymes and so bring about their destruction. As a matter of fact, such is the case, and under certain conditions zymase is attacked by the proteolytic enzyme of the yeast cell with the consequent destruction of its activity. There is a good deal of evidence, however, that in the living cell there exists a substance whose special function it is to protect the enzymes from this action. There can be very little doubt that the fermentative and other changes above referred to take place within the yeast cell, and that the alcohol and carbon dioxide having been formed in that wonderful little laboratory, then diffuse through the cell membrane into the surrounding liquid. Having given a necessary brief outline of the more important phenomena of fermentation, both in their biological and chemical aspects, we may now return to a consideration of the process from the more purely technological side. It will be remembered that to the cooled wort collected in the fermenting vessel the necessary amount of yeast is added, and fermentation is allowed to proceed, page 73. The fermenting tun in its simplest form consists of a square or round vessel, usually constructed of some suitable wood, but often lined with copper or occasionally at the present time with aluminum. This vessel is fitted with a coil through which cold water may be circulated for the purpose of controlling the temperature of the fermenting wort, and an arrangement known technically as a parachute, which is capable of adjustment in a vertical direction and which serves for the removal of the yeast formed during the process and its transference into the yeast bags or store vessels below. In Fig. 12, A is the attemperating coil, B the parachute, from the pipe C of which the yeast drops into a vessel on the floor beneath, and D a movable skimming arrangement for collecting and guiding the yeast into the opening of the parachute. In the simplest system, known as the skimming system, the fermentation commences and ends in the one vessel, the beer being racked either directly from this vessel into the trade casks or transferred to a racking vessel for purposes of convenience. In the latter, little or no fermentation occurs and the beer is rarely allowed to remain in it for more than 24 hours. One advantage of this vessel is that it enables the brewer when necessary to add sugar solution, or priming as it is called, in bulk instead of to the individual casks. In other systems of fermentation as practiced in this country, the first part of the fermentation only is allowed to take place in the original fermenting tun, after which the partially fermented wort is run into other vessels for the completion of the process, these vessels being either rectangular wooden vessels known as dropping squares or connected casks of special construction known as unions. The latter system is typical of the working adopted in the breweries of Burton-on-Trent, and the vessels in question are usually known as Burton unions. Other systems are in vogue, some of which are peculiar to certain parts of the country, but whatever may be the precise nature of the plant employed, the essential process is substantially the same, and consists in the conversion of the fermentable sugars of the wort into alcohol and carbon dioxide in the manner described above. The amount of yeast used by the brewer for the purpose of bringing about fermentation varies somewhat according to the strength of the wort and other circumstances, but may be given roughly as from 1 to 3 pounds of fairly solid yeast per barrel of 36 gallons. After the addition of the yeast, fermentation commences almost immediately, and at the end of a few hours the liquid in the tun will be found to be covered with a frothy or creamy layer. This rapidly increases in volume and a little later forms a fairly thick covering of very irregular surface, which is known as the rocky head. This in turn undergoes a change in appearance, becoming more compact in character and presenting a more even surface. At this stage the process of fermentation is rendered evident by the fact that the carbon dioxide rising to the surface of the liquid passes through this yeasty layer, forming large bladdery bubbles which quickly burst and are immediately replaced by others. To anyone watching the contents of such a tun the whole of the yeasty head or covering will be found to be in a continual state of motion, owing to the escape of carbon dioxide gas. At this stage the newly formed yeast is skimmed off for the first time, or the partially fermented wort is transferred to the dropping square or union in which the fermentation is allowed to complete itself. During the progress of the fermentation the temperature of the fermenting wort rises owing to the vital activities of the yeast, and has for several reasons to be held in check. From 60° Fahrenheit, at which it is customary to add the yeast, the temperature rises to about 70° Fahrenheit or 75° Fahrenheit, an increase beyond these temperatures being prevented by the passage of cold water through the attemperating coils above mentioned. It is not within the scope of this book to describe in detail the process of fermentation as practiced in the brewery, and it may therefore be assumed that the fermentation of the wort is completed and the liquid, now no longer wort but beer, is ready to be transferred to the trade casks or to be otherwise dealt with. From all that has been said above it will be clear that the essential feature of the fermentation process is the conversion of maltose into alcohol and carbon dioxide through the agency of the yeast organism. As stated on page 105, the maltose has first to undergo conversion by the enzyme maltase into dextrose, and it is in reality this sugar which is broken up and furnishes the alcohol and carbon dioxide. As fermentation proceeds, the sugar is of course replaced by alcohol, and the carbon dioxide simultaneously produced is liberated into the air, so that the specific gravity of the fermenting wort decreases continuously until the process is complete. This reduction of density is technically known as the attenuation, and as has been pointed out (page 37) is, within certain limits, capable of being controlled by the brewer during the mashing process. During fermentation the whole of the free maltose disappears, and it is also probable that some of the lower type of maltodextrins are degraded to maltose and fermented by the ordinary so-called primary yeast (Saccharomyces cerevisiae). At racking, therefore, the beer will contain the following substances: Products formed as a result of the fermentation process: 1. Alcohol. 2. Carbon dioxide. 3. A little glycerin. 4. Traces of higher alcohols, succinic acid, etc. Unfermented constituents of the original hopped wort. 5. Maltodextrins of various kinds. 6. The so-called stable dextrin. 7. Proteins and other nitrogenous substances not utilized by the yeast. 8. A little mineral matter. 9. Bitters and other substances derived from the hops. The above does not pretend to be a complete list, for beer contains many substances in minute proportions, but it is intended merely to show at a glance the more important constituents, and how these are roughly to be divided between the products of fermentation and those present in the original wort. Analyses of a few representative types of beer will be found in the appendix. At the moment of racking, the primary fermentation has spent itself, that is to say, the whole of the readily fermentable carbohydrate matter has been decomposed and replaced by its equivalent of alcohol. A reference to the above table will show, however, that it still contains a certain amount of carbohydrate matter, which, as has been pointed out on page 33, is necessary for the cask or secondary fermentation. Without this the beer would rapidly become flat and undrinkable, and the brewer endeavors by every means at his disposal to ensure that the proportion and the character of these residual carbohydrate matters, maltodextrins, shall be properly suited to the class of beer he is brewing, that is to say, shall be such that the beer comes rapidly into condition on the one hand, or undergoes a slow and protracted cask fermentation on the other. Whilst the higher type maltodextrins are not appreciably attacked by ordinary yeast (Saccharomyces cerevisiae), they are reduced to free maltose by the hydrolytic action of certain of the secondary yeasts, e.g. Saccharomyces pastorianus, and it is these yeasts which are largely responsible for the true secondary fermentation of stock beers. These yeasts are almost invariably present in very small proportions in the ordinary pitching yeast, i.e. the yeast added to the fermenting tun to start the fermentation, and are often conveyed to the wort from the air during the process of cooling. In any case they are rarely if ever absent from the beer at racking, although during the main fermentation they have been kept severely in check owing to the greater activity and enormous numerical preponderance of cells of the culture yeast. At the end of the primary fermentation, however, the latter begin to find the environment unsuitable, and the secondary yeasts, which are better able to attack the maltodextrins, come into play and rapidly increase in numbers. In the case of mild ales and certain other beers which undergo practically no storage, but are drunk within a few days of being racked into cask, these secondary yeasts are not needed, for the fermentation which takes place in the cask during those few days is virtually a continuation of the primary fermentation, and not a true conditioning in the strict sense of the term. It is for this reason that pure yeast, that is, yeast of a single species, has in such cases been found to give good results in English breweries, whilst for stock ales it has invariably proved unsuitable. Owing to the presence of the alcohol, the carbon dioxide and the hop resin, all of which are bactericidal in varying degrees, beer is not at all a favorable medium for the growth of the vast majority of bacteria. There are, however, some which are capable of thriving in it, and these may very easily give rise to disastrous results. The certain bacteria, prominent among which is the Bacteria aceti, promote the oxidation of some of the alcohol to acetic acid, and so cause the beer to become sour. In vinegar making, this organism is intentionally used for the purpose of converting the alcoholic wash into acetic acid, and, indeed, vinegar could be made from beer in this manner. Certain other bacteria produce traces of butyric and other strong smelling fatty acids, the presence of which, of course, renders the beer thus attacked quite undrinkable. Other bacteria again produce the condition known as ropiness, in which the beer has an oily appearance when poured from a vessel, or, in extreme cases, may be almost jelly-like in consistency. In practice it is impossible to brew beer under such conditions as entirely to prevent the introduction of bacteria, and all that the brewer can do is, by paying the most unremitting attention to the cleanliness of his vessels and plant, and by excluding all but filtered air from the wort during certain portions of the process, to reduce the infection to a practically safe minimum. Given a sufficiency of the preservative constituents of the hop, and a constant development of carbon dioxide, conditioning, beers brewed under such conditions will keep sound for many months, and in the case of strong beers, where the larger percentage of alcohol helps, for years. End of chapter 6. Of Brewing by A. Chaston Chapman. This LibriVox recording is in the public domain. Read by Marianne. Chapter 7. Distribution, including bottling. Speaking broadly, beer is supplied by the brewer either in cask, draft beer, or in bottle. At the present time the staple beer of this country is the so-called mild ale, which is intended for rapid consumption. This beer is supplied to the wholesale trade in cask, and is usually consumed within a few days of leaving the brewery. Whilst most well-brewed beer will become spontaneously bright if kept for a sufficiently long time under proper conditions, this beer is required to be brilliant within a very short time of racking into cask. To effect this, it is customary to add finings. Finings consist of a viscous solution of isinglass in dilute acid, usually sulphurous, or tartaric, or both. The isinglass, which is not really dissolved by the acid, but is only in a state bordering on solution, immediately coagulates, when the finings are added to the beer, and in the process entraps as it were all the suspended particles, carrying them either to the top or to the bottom, and retaining them in the coagulum formed. One of the most striking changes which has taken place in the brewing industry during recent years is the enormous development of the bottle trade, largely at the expense of small casks. Originally all bottled beer was conditioned in bottle, that is to say, it was allowed to mature for a certain time in cask, and was then transferred to bottles, which were stored for a sufficiently long time to enable the secondary, or in this case bottle fermentation to take place. Slow fermentation taking place under these conditions, that is to say, in the virtual absence of oxygen and under pressure, resulted in the production of a type of beer which could not be produced in any other way, and which was, and still is, highly appreciated by the connoisseur. The system is regarded by experts as in many respects the best, and it is still adopted in the case of the finest pale ales, export beers, and other beers of the highest quality. For a long time the bottle fermentation was thought to be due entirely to secondary yeasts, such as those which are chiefly responsible for the cask conditioning of draught beers, but during recent years it has been shown, first by Clausen, that certain organisms belonging to the group of Torulae are in reality the active agents. The Torulae are closely allied to the true Saccharomycetes, from which they differ chiefly in their inability to form ascospores. As compared with the yeasts, from which they are often indistinguishable in their microscopical appearance, these organisms (Fig. 13) have usually fermentative properties of low order, and many of them are incapable of fermenting the ordinary sugars, to say nothing of the comparatively stable residual carbohydrates of beer. Some, however, have this power, and it is highly probable that the characteristic flavour of certain bottled beers is to some extent the result of their activity. At the same time there is abundant evidence that the ordinary secondary yeasts are also operative. One objection to this system will be obvious, namely that since conditioning of the beer is due to fermentation occurring within the bottle, there must be a corresponding formation of yeast, that is to say, of sediment. About 30 years ago the practice of carbonation as applied to bottled beer made its appearance, and was soon found to meet a widespread demand. In this process the beer was bottled in a bright condition and was then charged artificially with carbon dioxide, as in the preparation of the ordinary mineral waters. From the brewer's point of view, it had the advantage of enabling him to do a much quicker trade and to increase his turnover, whilst the consumer was glad to get a bottle of beer which was always charged with gas, and which being practically free from sediment, involved no waste. This process, which is still widely adopted, and which has certain well-defined merits, is not technologically a very perfect one, for not only is it impossible to prevent effectually the occurrence of fermentation, and consequently of sediment, if the beer is not quickly consumed, but there is from time to time a certain amount of difficulty, due to the separation of certain protein matters of slight solubility. This is often a source of very considerable difficulty to the brewer, in draught as well as in bottled beers. Certain of these proteins, which cannot be assimilated by the yeast, and which consequently pass through into the finished beer, are frequently just on the borderland of true solution, and so a very slight alteration in the character of the solvent, such as the formation of a little more alcohol, or the presence of a little more gas, causes them to come partly out of solution. In this state they cause the beer to present a hazy appearance, which is very difficult to deal with, and which renders it for all practical purposes unsaleable. Even the most perfect filtration could not entirely eliminate these defects from the simple carbonation process, and so brewers were quite prepared to welcome the chilling system. The principle underlying this is a very simple one. The solubility of the more complex protein matters dissolved in the beer diminishes with reduction of temperature, and if the beer is cooled sufficiently, they will come more or less completely out of solution. If then the beer is submitted to filtration at this low temperature, these matters will be removed, and the beer will subsequently remain brilliant for a considerable time, even when exposed to the most adverse conditions. In some cases the beer is cooled slowly in bulk in refrigerating chambers, whilst in others it is cooled rapidly in cylinders, but in both cases it is forced at a temperature but little above that of the freezing point of water through special filters before passing to the bottling machine. When the beer is cooled slowly in bulk, there is a very perfect separation not only of the protein matters, but also of suspended yeast cells, and such beer will keep brilliant in bottle for a considerable time, provided that a thoroughly efficient filter is employed. Beer which has been quickly chilled is often less satisfactory in this respect. Unfortunately, the lowering of temperature has the effect of bringing out of solution not only the undesirable proteins, but also the hop resin, and beers which have been submitted to this process frequently possess too little hop flavour, a defect which has not up to the present been entirely remedied. Many modifications of these systems exist, but as the principles underlying them are practically the same, it will not serve any useful purpose to refer to them in detail. A certain amount of beer is sold in quart bottles or flagons, but as this is virtually draught beer, sold in bottles instead of in small casks, to suit the consumer's convenience, it is not necessary to refer to it further. It will be seen then that bottled beers may be roughly divided into three classes: A. Beers matured in cask and allowed to condition in the bottles. B. Beers filtered and artificially gassed in bottle. And C. Beers chilled, filtered at a low temperature and bottled with or without the use of extraneous gas. That the beers of the first class are by far the best is generally admitted, and few beer drinkers would be found to deny the statement that in the other classes of bottled beer brilliancy is usually secured at the expense of character and flavor, although, of course, there are great differences in these respects in the products of different firms. In concluding this chapter, attention may be called to the utilization of two very important waste products of the brewery, namely carbon dioxide gas and yeast. Taking the fundamental fermentation equation, C6H12O6 equals 2 C2H6O plus 2 CO2, it will be seen that 180 parts by weight of dextrose yield no less than 88 parts by weight of carbon dioxide, or for every ton of sugar fermented nearly half a ton of the gas is liberated. In many of the larger breweries this gas is collected from the fermenting tons, purified by passing it through scrubbers and towers containing certain purifying agents, and then condensed, cooled, and liquefied. The liquid carbon dioxide is then transferred to stout cylinders from which it is used by the brewer himself, or in which it is sold to other brewers or to mineral water manufacturers for the gassing of their products. Yeast is another byproduct of the brewery, to the utilization of which a very large amount of attention has been devoted during recent years. Under ordinary circumstances, a reproduction equivalent to about 5 times the weight of the yeast used for pitching occurs; that is to say, for every 1 pound of fairly solid yeast added to the ton at the commencement of fermentation, about 6 pounds of equally solid yeast will be recovered. Assuming 30 million barrels of beer to be brewed annually in the United Kingdom, and assuming further that 5 pounds of yeast will be obtained from each barrel fermented, it will be seen that the whole annual output of yeast for the United Kingdom alone would amount to no less than 67,000 tons. Of this, which is undoubtedly a very low estimate, a proportion is of course needed by the brewer for starting fermentations, but the great bulk is not so required and is available for other purposes. Of the various uses which have been suggested for the product, by far the most interesting and successful is its conversion into a food product. It will be remembered that the yeast cell consists largely of protoplasm, the chemical basis of all living cells, and it is clear that it should possess nutritive properties of a high order. By a patented process certain changes are effected in the protein constituents, and as a result a product is obtained which resembles extract of meat so closely that it is almost impossible to distinguish between them either by taste or smell. In chemical composition, moreover, they are very similar indeed, the only difference so far as is known, being that meat extracts contain the bases creatine and creatinine, whereas yeast extracts do not. As feeding stuff for cattle, dried yeast is also being somewhat largely used. End of Chapter 7, and end of Brewing by A. Chaston Chapman, recorded by Marianne Spiegel in Chicago, Illinois, in July 2015.